Okay. So let me review just do a little bit of reviewing. What we're going to do, we're going to start out with Coulomb gauge quantization. As I said last time, when you're in a gauge theory, you quantize the theory by first picking a gauge, and then in that gauge you quantize the theory. And the most physical gauge for quantum electrodynamics is the Coulomb gauge, which says that the divergence of the vector potential is 0, and that means that you've just got transverse photons. The action density is minus a quarter FAB, and plus JA, where J is some current. The equation of motion is dB FBA is minus JA, and there are the homogeneous equations. dA FBC plus cyclic permutations, dB FCA plus ECF AB. Some of the things are 0. I should have said what FAB is. Or FBA is dB AA minus dA AB. This choice of sign varies from one physicist to another, sometimes from one page to another. That's not a thing, obviously. One of the field equations, this one in particular, is just minus DI EI, and that's minus J0. This is Gauss's law, del dot E is rho, which is J0. And the result is that we have a field equation, grad squared A0 minus D0 of del dot A, which is del dot E is J0. So this is true in an arbitrary gauge. In Coulomb gauge, this term is 0, and consequently you have grad squared A0 is J0, and this gives A0 of X and T. An integral of J0 y and t d cubed y over 4 pi x minus y. So this is a review of what we did last time. And so the quantum fields are the transverse parts of A. So I might write it like that. So those are two fields. And the corresponding transverse part of the electromagnetic field, this is effectively the momentum that's conjugate to the transverse electromagnetic field. Weinberg goes through this in great detail using brackets and so forth. I'm going to let you read that on your leisure if you want, but I think we need to move forward more quickly. And in any event, Weinberg says that right way to do all this. The more convincing way is to use path intervals, and so it's starting to look as though we should really base physics on path intervals rather than on quantum mechanics. Anyway, if we're doing, now we're going to do perturbation theory. So we write the Hamiltonian as H0 plus B. H0 is a half an integral of B squared plus B squared E cubed x, and these of course are transverse, and then plus some matter Hamiltonian, the free part of the matter Hamiltonian, and then V is minus J dot A T cubed x plus a Coulomb term, and then plus some, possibly some matter interaction Hamiltonian. And B, of course, is the curl of A, and even if A were not transverse, B would automatically be transverse. That's one of the reasons why the Coulomb gauge is a physical gauge. The Coulomb potential energy is just an integral of J0, A0, or actually they're both upper. And so it's actually a half integral J0 of x and t, J0 y and t, d cubed x, d cubed y, and 4 pi x minus y. Okay, so that's the Coulomb potential energy. The electromagnetic field is what you'd expect. A b of x is an integral d cubed p over this square root of 2 pi cubed, 2p0, the sum over the two polarizations, e to the I px. The bth component of the polarization vector, the momentum p and the spin s. A deletion operator for photon of momentum p and spin s. And then the creation part, EB complex conjugate of p and s. A dag, oh no. Yes, a dagger, sorry. For the moment I was talking about fermions. Okay, so that's our electromagnetic field, and these vectors EB are ones that we've kind of seen before. There's a rotation operator that takes you from the z direction to the p direction, and they act on 1 over root 2. A0 is 0, 1, plus or minus I, and 0 in the 3 direction. So these are transverse in the sense that, well, always it will be true that p vector dot e of p and s will be 0. So that's the transversality condition, which is automatically satisfied by this construction, because you see this is the polarization vector for a photon in the z direction. The polarization vector, the momentum for the z direction would be, would just have a 1 here, or equivalently, if you had the, you could also do p dot e of p and s that's also 0. There, E0 is 0, and so P0 doesn't contribute. Okay, I think these are the preliminaries. So just one more time, E0 is equal to 0, and it's also, and that means that A0 is equal to 0. So this is again because we're doing things in the Coulomb gauge. And of course the annihilation and creation operators, equivalently the absorption and deletion operators, obey the usual commutation relations, delta S prime, delta Q, P minus P prime. Okay, the Hamiltonian is one that's very similar to one that you did in the homework problem. It's an integral, a sum over S, P0, A dagger of P and S, A of P and S, plus a half, delta 3 of 0, and then that whole thing is integrated dQt. And the interaction is V of T is equal to, we're in the interaction picture, so we move things along with the free field time dependence. We have then minus J of x and 0 dot A of x and 0 equal x. And then there's a Coulomb term, which is J0, A0 over 8 pi x minus y, p cubed x, p cubed y, and then if there's some matter interaction, it's there, and then e to the minus I h0 q. So that's our interaction. Okay, now I'm going to do the photon propagator, and there's the long story and the short story. Let me give you the short story first. That's the sweet part. The propagator which you can write as minus dAd of x minus y. This is simply going to be d4 q over 2 pi to the 4th minus I eta AB over q squared minus I epsilon e to the iq x minus y. So it's perfectly covariant, and so this is what will, this is the mean value in the vacuum of A sub A of x, A sub B y vacuum, and I'm going to write effective here. The point here is that what we'll start doing now in order to get to this is we'll use the Coulomb gauge electromagnetic fields, and we'll see that this, we can massage this into something that cancels in various ways, and then this is the remaining term. So relativity is restored, whereas this interaction here is pretty crazy, and the Coulomb interaction is an embarrassment if you're thinking in terms of relativity. special relativity. Okay. All right. I think the appropriate thing is to jump ahead. Well, maybe not. Maybe instead of jumping around. Oh, I was on the wrong page in the notes. Okay, so let's now compute this. Starting from here, basically. And what we'll get then is minus I delta, well, Ij of x minus y, because after all, the electromagnetic field in Coulomb gauge has no time component. And if we use our formula for the electromagnetic field, namely this expression over here, we see that for b equal to 0, it's 0, so we're just dealing with space components. This, and we just plug it in and crank the way we were cranking a week or two ago. We get dq, 2 pi q, 2p0. Remember, the spin sum is delta ij minus pi pj over vector p squared. And then what we have is e to the I px minus y, theta of x0 minus y0. Weinberg leaves out the zeros because it just assumes you know it's a time component. It's the theta function is the time component, but I'm going to put them in. And after one does that integration, what one finds is an integral d4th q over 2 pi to the 4th minus I over e squared minus I epsilon delta ij minus pi j over p vector squared. Well, q, sorry. Okay, I've screwed up all over here. Don't copy that down. I need to follow the notes here. This is qi qj over q vector squared. E to the iq x minus y. All right, now we're going to massage this. What we're going to do is we're going to introduce a 4-vector n whose components are simply 1, 0, 0, 0. So it just has a time component. And then we're going to do something really weird. We're going to write this in a funny way. We're going to write it as delta AB minus QA QB over Q vector squared times theta AB. This is kind of silly, but it means that the thing is 0 when A of B is a time component. Oh, wait. Well, this is sort of ambiguous, isn't it? All right, let me just say. All right, I mean, it's okay to have it as theta AB, but I'm understanding now that the theta function is this theta of 0 is 0, and theta of 1 and so forth is 1. So the theta function goes from 0 to 1. I'm having it at 0 be strictly 0. And of course, these are just integers, so it's I suppose we need an integer value theta function, or a theta function that depends on an integer variable. Anyway, we can rewrite this as A to AB plus Q0 times QA NB plus QB NA minus QA QB plus Q squared NA NB. All of that in the numerator and Q vector squared in the denominator. So that's just a, as Weinberg says, this is a perverse equation. It's rather absurd to take something that's kind of nice and write it in this very absurd way. But
can I ask, I'm sorry, first I'm confused about the theta AB, and then also why are the two?
I'm just saying the left-hand side is 0 and A or B is 0. That's what the theta
Okay.
means.
Sure, okay.
And now on the right-hand side, A and B can be 0, 1, or 2, or 3.
Okay.
And N is just this funny vector that has 1 in the 0 component, 0 otherwise.
Okay. And wait, so we're using.
And so this is just an algebraic identity.
Okay. And we're using this because above is this expression that we have.
Yeah, these are just I and J are just positive integers.
Yeah,
1,
so
2, or 3.
If they're both 0, are they going to be 0 or something? Yeah, I don't know. Yeah, man, I'll just have to wait and see how this comes back. I guess I'll just have to wait and see how this comes back and how we can make this useful in this expression that we have.
Well, these two things are the same.
Okay, yeah, so the thing above, is it 0 whenever I and J are both 0?
Yeah, whenever I and J are 1, 2, 3 in this equation.
Oh, they're 1, 2, 3. Okay.
Yeah, because they come from the electromagnetic field. Mean time-ordered product. And in other words, what we're doing is this.
Yeah.
Okay.
Oh, the I and the
if
J.
A or B is 0, the thing is 0.
Yeah, because that's 0 time.
Right.
Yeah, I see.
So, and in a sort of tour de force, we can write that down, check that it actually works. Now, suppose we did that. Suppose we took this and use this instead of that in the photon propagator and calculated our S matrix and Feynman diagrams and so forth. Well, always the electromagnetic field is coupled to some current JA, and dA JA is 0. So the electromagnetic field is always coupled to a conserved current. That's the matter field that it's coupled to. And so what happens? These Q's, as you know, momentum corresponds to differentiation. And so these effectively play the role as derivatives. The derivative then multiplies the J and you get 0. So effectively, if you use this to calculate S matrix elements, this one gives us a 0 because of that. This one gives us a 0. This one gives us 0 squared. And we're left with this one. But this one only has, it works for both of them equal to 0. Now what happens to that one? Well, let's write it down. This last surviving term is Q squared NA and B over Q vector squared, and it multiplies minus I over Q squared minus I epsilon. So here, the two Q squareds cancel, and what we get is minus I NA NB over Q vector squared. So that's what's left over. We missed it. So what does this give in the S matrix? Well, it gives the following term. A 1/2 integral d4th x, d4th y, and there would be minus I j0 of x, minus I j0 of y, minus I over 2 pi to the 4th, integral d4th q, e to the I q x minus y, over q vector squared. So that's what this term would give if we cancel out these two. We use this term for that in the propagator, and we have the minus I q squared minus I epsilon and so forth, and the Fourier factor. Well, if you do the integral over q0 gives us a delta function. And so this becomes I over 2 d4th x, d4th y, j0x, j0y, d cubed q over 2 pi cubed, delta of x0 minus y0, e to the I q dot x minus y, and q vector squared. And now if you do the y0 integration, you get I over 2 integral d cubed x, d cubed y, dt, j0 of x and t, j0 of y and t, over 4 pi x minus y. And this cancels the term that arises from this term in the interaction density. In other words, when you do the S matrix with this propagator together with the Coulomb term in first order perturbation theory gives you a term that exactly cancels this. Because it would be this thing times minus I integrated over time. And so the upshot is that what we're left with is simply the A to AB. And that means that we take this propagator and replace this by A to AB. And so that gives us what I wrote down to begin with is the sweep propagator, which is minus I A to AB over q squared minus I epsilon and so forth.
Tim, so this t that you wrote here?
The what?
So you wrote t equals this thing. What you're calculating here is you're calculating some term in the S matrix at second order? Is that the idea?
Yeah,
you
yeah.
expand the S matrix and you
That's
second
right.
order. And that's from the J dot A term, right? Is that what this is from, the original J dot A term? Or no, it's from the J0 A0 term? Sorry, I mean, you're saying like, oh, this term.
Oh, no, this term.
Something else. What?
This
like,
term.
Where did this come from?
The idea here is that, well, as I said to you, the whole point is that AAJA is the way the electromagnetic field appears, and so this term A to AB in a Feynman diagram would have a J0, a JAAA, and in particular, if we, in other words, if we use this term in here and use this as the photon propagator, use this as the photon propagator, then the 0, 0 term would give us this. That cancels the term we don't want.
Also, I'm wondering, like, why do we even have that term in the first place if we said that
This
A0,
one?
0? But it wasn't A0, 0?
This is a 0, 0 term. Well, it's a 0, 0 term, but where are we here? You see, the actual interaction is J dot A plus VC plus V psi. In fact, that's what I should have written down. Why did I write down? I think I got switched. No, you see, this is VC.
Yeah, J0, A0 term.
In the energy term, in the Coulomb gauge, this is the Coulomb term. This is just the electrostatic energy of a charge distribution. And that's there, that's part of the interaction Hamiltonian. And so it sits up here, and it's, and you can write it as A0. I should have written it as, in fact, I think that's actually a mistake. Let me just, yeah, I wasn't even reading my notes correctly. That's a mistake. That was J0, J0.
Okay.
So let me give you, in fact, you get 2 candies drawing my attention to that. Okay, so that's, so in other words, this term is an embarrassment, as I've said many times. But on the other hand, this other term, which is an embarrassment and is left over, gives a term that cancels the embarrassing term. And the upshot is you do the Feynman diagrams with just this manifestly Lorentz invariant term.
Okay. Sorry, Kevin, I'm sorry to keep asking this. Why? So why do we even have this term in the first place? Because my confusion is that where this is coming from. So yeah, I'll just make a point. What this is coming from, with this term, the J0 over X minus Y, is coming from A0, right?
Right.
Because that's
And,
exactly
and the point is, we were able to solve that because Gauss's law is a constraint.
Yeah, but then we write this, right? Then we write A0 as 0.
That's
right?
this field.
Okay.
That's this field.
Okay.
Once we set A0 equal to this, A0 is gone as a field in the
Okay.
problem. It's not a quantized field.
Okay.
It's just an it just disappears, and the only relic of it is the electrostatic energy of a charge distribution.
Okay.
So the electromagnetic field from that point on has no time component. That's why these things are only space components. And on the other hand, this elaborate reverse manipulation shows you that, in fact, these terms actually don't, these actually cancel, except for this one. This one cancels that one. We're left with this one. And so we can just replace this by A to AB, where A and B now can be 0, or it can be time or space. Now, this is something of a hand-waving argument, which you sort of saw by the fact that I was gesturing so much during this discussion, rather than just writing with chalk and droning on. A better way of doing it is path integrals, but we're not going to get to path integrals for another week or two. Let me in order to get to path integrals, let's just go through the Dirac action density. It's minus psi bar gamma A dA plus m psi. This is the 4-component spinner. Psi bar, remember psi dagger gamma 0. And I guess you remember that gamma A, gamma B plus gamma B, gamma K is 2 eta AB. And let me just mention that if we try to do things actually rigorously. The partial of the action density with respect to psi dot is minus psi bar gamma 0, which is I psi dagger. The Hamiltonian for the Dirac field then is an integral of pi psi dot minus L d cubed x. And so this is an integral of I psi dagger psi dot plus psi bar. Let me just write this as E slash plus M psi. You remember the slash notation? A slash is simply gamma A, AA. Now what happens is, actually I shouldn't have slashed this because now it obscures what the D0 gamma 0 is. But if you put back D0 gamma 0, you see that the time derivative terms cancel. And the actual Hamiltonian for the Dirac field is an integral of psi bar gamma dot grad plus M psi d cubed x. And if you, and I should write this as H0 because what we're talking about is the free part of this. And if we write psi of x, well, as we've been writing it a few weeks ago, 2 pi to the 3 halves, sum over spins, u of p and s, e to the I px, a of p and s, plus v of p and s, e to the minus I px, e dagger of p and s. So if that's our Dirac field, where the absorption and addition operators or annihilation creation operators obey the anti-commutation relations, and the same thing with B, so I'll just write them like that. So they obey these anti-commutation relations. You then take this thing and put it in there, and you find that this is actually an integral, a sum over spins, P0 of a dagger of P and S, A of P and S, plus B dagger of P and S, B of P and S, and then minus delta cubed of 0, P cubed P. And you notice that the awkward, embarrassing, infinite term in the Hamiltonian, because we're dealing with fermions, it comes in with a minus sign. And that's one of the reasons why people like supersymmetry. Because if you imagine that your actual theory is supersymmetric, then for every boson mode, there's a fermion mode. Every boson mode comes in with a plus sign. Every fermion mode comes in with a minus sign. And these horrible infinities, which are the worst infinities that I know of in quantum field theory, they all cancel. The problem with this solution to the problem of infinities is that there's been no experimental evidence in the half century or so since supersymmetry was invented, there's no experimental evidence in support of supersymmetry. So we're in a situation where it'd be nice, but supersymmetry must be broken, and it's apparently broken, if it's relevant at all, it's apparently broken at higher energies than people thought, because it's still not observed in neutron dipole, neutron electric dipole, electron electric dipole, or LHC experiments. And so we've got this huge puzzle, and nobody knows what to do about it. Okay, so let me now tell you what Feynman's rules are for QED. And so let me first of all write down what we're dealing with. Minus a quarter FAB, FAB, minus psi bar. I was going to ask you to use your pen, but obviously I can't. Psi bar d slash, well, actually it's not d slash, gamma a dA plus I a sub a plus m psi. So this is the action density for QED, quantum electrodynamics. This is the electromagnetic field mass of the electron, and you see this is the covariant derivative. And in fact, people often write this as psi bar big D slash plus m psi. So that's the way people sometimes write it. The electric current here, JA, is the partial of the action density with respect to A lower A, and this is minus IE psi bar gamma A psi. And okay, so what are Feynman's rules? First, draw all diagrams, and let me say that I'm gonna try to apply them now and compute some scattering amplitudes, and you will see that if you use these Feynman rules, these elaborate computations, the Feynman rules reduce them to just a few minutes work, and so they're, for that reason they're really celebrated. So you first draw all the relevant diagrams. I'm going to be talking then about electron-positron scattering. So there are two diagrams. One looks like this. So electron in, positron in, photon, electron out, positron out. And so I label these as P, K, P prime, K prime, and this thing would have Q, and Q would be equal to P plus K. But there's another diagram, and the other diagram is P in, P prime out, photon across, and positron out, positron in. And as I've said to you, or as you've noticed in the past, the antiparticles have arrows that are opposite to those of the particles, and it's kind of it's as if they were moving backwards in time, which was Feynman, one of Feynman's remarks. By the way, I read a quip that was attributed to some computer scientist. He was talking about artificial intelligence, and he said that the problem, many people say the problem with artificial intelligence is that it's too intelligent and it's going to displace humans, be a threat to mankind. He said, instead, the actual problem with computers is that they're too stupid and they've already taken over the world. Right? I said it absolutely, I said it poorly. The quote, I should have read the quote, but I don't have it in front of me. It's in the New York Times today. What he actually said was, many people think that computers are too smart, are so smart that they're taking over the world. He said the actual problem is that they're too stupid and they've already taken over the world. All right, well, I've blown it. So much for my career as a stand-up comic. Okay, so the Feynman rules are, first draw your diagrams. So this is electron-positron scattering, which we would write as E minus plus E plus goes to E minus plus E plus. There's another process which is E minus E plus goes to muons in the final state. Well, if you have muons in the final state, this diagram doesn't appear. And so you just have this diagram, so it's a simpler process. This is called the direct or annihilation diagram. This is called the exchange diagram. Has nothing to do with stock exchanges. I guess I don't know why it's called exchange. Anyway, all right. What are his rules? So rule 1: each vertex you write down 2 pi to the 4th E. That E. Gamma A, beta alpha. So this is a gamma matrix, and you have beta alpha, and the beta is, for example, here it would be beta and alpha, like that. And then you put in a delta function of P minus P prime plus Q. So that's what we're this is really for this particular vertex. For this vertex, it would be P plus K minus Q, and the beta and alpha would refer to these, it would be alpha, beta, like that. Anyway, the gamma is associated with the vertex, this vertex or that vertex. And then, okay, so that's the first rule. The second rule is outgoing electron line, U bar beta, P and S over 2 pi to the 3/2. Outgoing positron, you have V alpha of P and S over 2 pi to the 3/2. Incoming electron line, U alpha P and S over, again, 2 pi to the 3/2. Incoming positron line, V bar beta P and S over 2 pi 3 halves. Okay, so I'm out of board space. Let me go to the whiteboard and see what I can write down there. Now, although we have these marvelous Feynman rules, nothing prevents you from just using first principles, so you can also do that. Okay, then we have outgoing photon. And that gives us an E star A of P and S over square root of 2 pi cubed. So notice that it's always 2 pi to the 3 halves, and then 2p0. Incoming photon EA P and S over square root 2 pi cubed 2p0. Then internal lines. These are trickier. If it's an internal line of momentum p from a vertex beta to a vertex alpha, it's minus I over 2 pi to the 4th, minus I p slash plus m alpha beta over p squared plus m squared minus I epsilon. And as I mentioned to you, the minus I epsilon only matters when you're dealing with loop diagrams. For an internal photon line going from or linking vertices A and B with momentum q, you get minus I over 2 pi to the 4th, A to AB over q squared minus I epsilon. And the rest of it is add up all the terms. Integrate over all momenta, sum over all indices, add up all terms, get the combinatorics and the minus signs right. So that's the whole 9 yards. So let me first of all do the annihilation diagram, or the direct process for E plus E minus scattering. It's a lowest order, of course. Remember that E squared is actually such, this is the charge of the electron, and this is E squared over 4 pi, 0, the electric constant, H bar and C. This is 0.07297, and Google today gave me another 5 digits, but I'm going to leave them alone. It's approximately 1/137, so that's what, and this is called the fine structure constant, and it's often written as alpha. Alpha is the fine structure constant, and so for interactions at low energies, it's roughly 1/137. Okay, so now we're going to try to, I'm going to show you how these rules are essentially instantaneous. They give you the answer essentially instantaneously. And that's why when Feynman published them or told people about them, he became an instant celebrity in the theoretical physics community. And of course, justifiably so. And this was not the only thing he did. He did very, very many things. So integral d4th q. So that's the integration over everything. And of course, we need to be summing. So I'll put in a sum and I'll be a little vague over, well, I'll say we're summing, well, whether we're summing over spins or not depends upon what process we're talking about. And in fact, one of the things that is true here is that if you don't sum over initial spins and final spins, then the end of the calculation is, or at least an intermediate pause, or the end of the first stage of the calculation comes very rapidly because you don't do any sums over spins. And so that's what I'm going to do now. So for each vertex you put in this factor. So we've got 2 pi to the 4th E gamma A beta alpha delta 4th, and in this case, looking at the diagram, we see it's P plus K minus Q, because Q is going out, that's the photon going up. Then the other vertex, we put in 2 pi to the 4th E gamma B, and now I'm going to put in gamma delta as the indices, and then delta 4th, and now P prime and K prime are going out, so I've got minus P prime minus K prime plus Q. Q is going into that upper vertex. So what we're talking there about is P, K, P prime, K prime, P plus K. So that's the picture. And this is vertex A, and this is vertex B. So I've used the rule 1 twice because there are 2 vertices. And now what we've got is we've got the 2 outgoing fermions, and so we put in a U bar, and I'm going to use alpha and beta for the indices here, gamma delta for the indices there, the way I did it here. And so this is going to be U bar gamma of P prime and S prime, V delta of K prime and T prime, and each of these is divided by 2 pi to the 3 halves, 2 pi to the 3 halves. And now we have the incoming electron and positron, and so what we have is U alpha of P and S over 2 pi to the 3 halves, and V beta bar of K and T. This is incoming 2 pi, 3 halves. And then we have the internal photon line, and so that's minus I over 2 pi to the 4th, A to AB over Q squared minus I epsilon, although you can forget about the I epsilon. So that's how easy Feynman's rules are, and that is the amplitude right there, and you don't need to futz with it anymore. You do the Q integration, you use this delta function that says that Q is P plus K, and so what we get at that stage is 2 pi to the 4th E gamma A beta alpha 2 pi to the 4th E gamma B gamma delta, and now we're left with simply Q replaced by P plus K, so this is just conservation of energy and momentum. And then the rest of that is what we had before. You U bar gamma, P prime, S prime, V delta, K prime, T prime, U alpha, P and S, V bar beta, K and T, and I'm just going to divide this by 2 pi, let's see, 3/2, 6, instead of writing all the 2 pi's. Okay, now we combine these things with the gammas and so forth, and or at least we write them that way. So we can write this as, well, first of all, let's do the 2 pi's. We've got 2 pi to the 4th, 2 pi to the 6th, so it's 1/2 pi squared. There is, oh, I left something out here, minus I, right, minus I over 2 pi to the 4th, A to AB, and I'm just going to write this as Q squared. Oh no, it's not Q squared now, it's P plus K squared. I really need to follow my notes rather than drone on. Okay, now we can sort of reshuffle these things a little bit. And what we get is E squared V bar beta at K and T gamma A beta alpha U alpha of P and S, and then U bar gamma P prime S prime gamma beta gamma delta V delta K prime T prime energy momentum conservation, P plus K minus P prime minus K prime, and then times minus I over, and now if we look at the 2 pi's, 2 pi to the 10th in the denominator, no, those 2 pi's, oh God, where are my 2 pi's? Oh. All right, we started out with 2 pi to the 8th, and then here we had 2 pi to the 6th and 2 pi to the 4th. So altogether, it's 1/2 pi squared. So in between, I screwed up the 2 pi squareds, and then A to AB over P plus K squared. All right, so I've got the 2 pi's right there, but oh, they're right here also, 2 pi to the 8th, 2 pi to the 10th. Okay. So that's all right as well. And now we can rewrite this using matrix notation, and if we do that, we get minus I E squared over 2 pi squared delta 4th of P plus K minus P prime minus K prime P plus K squared, and then okay, I'm gonna jump to an abbreviated way of writing this right now. I'm going to write this as V bar gamma A U and this A to AB, I'm going to contract this gamma and make it, instead of gamma upper B, I'm going to make it gamma lower A by summing over B. And so this then is U bar prime, meaning it's P prime, S prime, gamma lower A, V prime. So that's the amplitude, and so you see these Feynman rules just bingo get you to the answer with, well, effortlessly, less effort than it takes to say effortlessly. Yes.
I read in this other book about, depending on the Feynman diagram that you're working with, you may have to divide by something called like a symmetry factor. Do we encounter this here?
A what factor?
Something called the symmetry factor. It sort of accounts for the number of ways that we could like permute.
Yeah. That's what I meant by combinatorics.
Okay.
No, it doesn't occur here.
It doesn't occur here.
No. And the reason is, in fact, the basic rule is that, or rule of thumb, I should say, is if in the action density you have, say, 3 or 4 fields that are all different, then the combinatorics are very simple.
Okay.
There aren't any. And so here we've got psi, psi bar, and A, 3 different fields. The place where you have these curious combinatorics is if you have 5 to the 4 field theory. So you have the same field, 4 choices, and that can be confusing.
I see.
Let me now say that once you've gone through and computed this, you can eyeball the other term. What would the other diagram be, the exchange diagram? Well, what it looks like is this. Let me go to the other. Let me flip or maybe I should leave this here and go to the blackboard, and I'll erase, and since I'm erasing something that is we only have a few minutes left, so let me just okay, so let's look at the diagram in question. The diagram in question is P prime, in fact P and S, P prime, S prime, photon line, so it's the exchange diagram. You can see that the momentum here will be P minus P prime. And so, and moreover, these vertices are a little bit different. This vertex here would be U bar prime, gamma AU, and this one would be V bar, gamma A, V prime. The propagator would be P minus P prime squared. And everything else is the same. Minus I, E squared over 2 pi squared. and then delta 4 of P plus K minus P prime minus K prime. And so what you have to do is you add the two together, and so the total amplitude then is minus I e squared over 2 pi squared, delta fourth of P plus K minus P prime minus K prime. And the first term that we did carefully was V bar gamma AU, U bar prime, gamma A V prime over P plus K squared. And this one is U bar prime gamma A U V bar gamma A V prime over P minus P prime squared. So that's the total amplitude. Now, suppose we wanted to get a cross-section. Well, remember, these are 4-component spinners, which I'll remind you, Weinberg actually did correctly. So in general, if you imagine that you're doing a procedure where you know the spins as well as the momenta of the incoming particles, and you're also measuring the spins of the outgoing particles, then what you have to do is you have to compute this, take the absolute value squared, and you then proceed with Fermi's golden rule and so forth, as Weinberg describes in chapter 3. However, and that's rather complicated, and in fact, you might be better off writing a computer program to do it for you than to actually do it yourself with your fingers. Or equivalently, you could download one of many computer programs. There are all kinds of available computer programs for these things. On the other hand, what is normally true experimentally is that you don't measure any of the spins. And so what you do is you average over the initial spins and you sum over the final spins to get the cross-section. And that means that you sum over initial spins, sum over final spins, and divide by the appropriate factor for the initial spins to average them. And then that means when you sum over spins, you've got things like U bar summed over spins, and here it looks a little bit more awkward here because I don't see a UU bar that is playing a role. Anyway, you have to use the spin sums that we talked about a few weeks ago. And Weinberg does Compton scattering in detail in his text. And so Compton scattering, as you know, you have an electron going in and a photon going in. And then you have an electron going across and the electron going out and the photon going out. And the other diagram is electron in, photon out, electron across, electron out, photon in. So you add those two diagrams, and Weinberg goes through the application of the Feynman rules to this case and shows you how to do the spin sums and so forth. I think it would probably be useful for me to do that in class on Thursday, to just sort of sketch it at least. By the way, Compton's paper in Phys Rev back in, I don't know, 29 or something. It's quite a nice paper. In fact, when I did my seminar in physical English last semester, I used it as one of the examples of good writing. What is interesting is some things that he said. I don't think he said them in his paper, but he might have said them in his paper. Namely, the amount of resistance he ran into from other physicists when he explained his result, because people didn't believe him. So in other words, they did not believe that photons would behave like particles, even though Einstein in '05 had explained that they did. So this was 20 years later, and the resistance was major when he gave a talk at the American Physical Society or someplace. All right, well, we're out of time, so I might as well just. Is there a final question?